Jack Jackson. We're back with some more integration exercises. So here we have several different examples. Problems 10 through 15 are antiderivative problems or indefinite integral problems. Problems 16 through 18 are definite integral problems that we can solve using the fundamental theorem of calculus. So what I'd like you to do here, if you haven't done this already, is to stop this, write down these problems, go work them, and then come back and check them. Or at least maybe write one down and work it, and then come check it with the video, and then write the next one down and work it, and so forth. So it's very important that you try some of these yourself. But this video will give you a way to check them as you go along here, and it gives us a pretty good introduction to some types of substitution problems that we might use using our basic rules that we've learned so far for finding antiderivatives. Okay, I'm going to ask you also to check your work, and you're going to check your work by taking the derivative of your answer and making sure that it is the original integrand right here in the antiderivative part. And of course you can do the same thing here to check a definite integral, to check that part of it. To check a definite integral, you can actually put this in your calculator as a numerical integral and check it. And of course we have a way of checking antiderivatives in our calculators as well. So use your calculators as checks, but be sure you do these without a calculator first and see what you can get there. So we're looking for exact values, not just decimal approximations for these definite integrals, which will be a number. And we're looking for formula, which will be a family of antiderivatives. Don't forget the plus c at the end. Okay, so let's get started with this. And exercise 10 was the antiderivative or indefinite integral of e to the negative 5x dx. So see if you can go ahead and work that one now and come back and check your answer. Well, if you're coming back now to check your answer, let's take a look and see what you have here so far. So we have a constant base to a variable power. So anytime you have a constant base here, remember e is a constant, specific number, and the variable base, more complicated thing, negative 5x, that's a good chance or a good indication that maybe that variable power could be our thing that we substitute for. So let's let u be the negative 5x. So we write that down to the side first, and then you take the derivative of this, and we get du is negative 5 and then dx. Now, remember, du really means du over dx times the dx. So this is what we call differential notation here. Now, in this particular case, we have the dx, the du, but we don't have the negative 5. And what we can do here in this case is insert a negative 5 multiplied together. Notice the parentheses. As long as we also multiply by 1/5 right here. But the 1/5 being a constant, by the constant multiple rule, can be brought out front of the integral sign here. So that 1/5, negative 1/5, and that negative 5 actually cancel each other out, and we're back where we started. So that is a legal thing to do. And then notice what's in parentheses here of negative 5 dx. All of that becomes the du. And the negative 5x becomes the u. Okay, so what happened to the negative 5 and the x? It became u. What happened to the negative 5 and the dx? That became du. And where did that negative 1/5 come from? It came something we inserted in the problem to balance the negative 5 that we really needed to insert in the problem to find our du. Okay, well, the hope is after you do a substitution that you get something that's more easily worked out. And in fact, we do know the antiderivative of e to the u du is just e to the u. We still have it times the negative 1/5, So we have negative 1/5 e to the u. When your last integral sign disappears, don't forget to put the plus c, because any constant we put here would be an antiderivative then of the original. Now we have the antiderivative, but it's in terms of u. Substitute, that's something that wasn't in the original problem. So we need to go back now, and we say u is negative 5x. We substitute that back in, and our final answer is the family of antiderivatives of e to the negative 5x dx is negative 1/5 e to the negative 5x plus c. Okay? Let's do another one. Here's number 11. The antiderivative, family of antiderivatives of 3x plus 5 in parentheses to the 42nd power dx, or the integral, indefinite integral, of 3x plus 5 to the 42nd power dx. See if you can work that one on your own. All of these exercises here in this little set will require some form of substitution. So see if you can figure out what the right thing is to substitute and work this out on your own. Press pause now. And now you're back. And so let's see if we can see what we should have gotten there. So hopefully it's maybe fairly obvious what to do here, but if not, let's look at this. What gives us a clue here? The base is a variable expression, not too complicated, but more complicated than, say, just an x. But the power is a constant, 42. So when you have a variable base and a constant power, one thing to try is to let the base, that variable base, be u. So let u be the 3x plus 5, then we write that on the side. Then we have to figure out what du is. Well, du is the derivative of this times dx. Well, the derivative of 5 is 0. The derivative of 3x is just 3, and then we put our dx. So du is 3 dx. Well, once again, we had the dx, but we didn't have the 3. So we put the 3 in here. We balance it with the 1/3 here, which we bring out front of the integral sign. Now, if we group the 3 and the dx together, that becomes du. And the 3x plus 5 grouped together becomes u. So we end up with u to the 42nd du for our integral, and then we have the 1/3 out front. Well, now this is just a power rule. So that's the idea why if you get a variable base and a constant power, you let u be the base, you're shooting for the power rule. And we achieve that here. Now the power rule says for antiderivatives, remember, be careful which direction you're going, whether we're doing derivatives or antiderivatives. Notice this part on the side here, when we go from u to du, we're doing a derivative. Right now, we're doing an antiderivative of u to the 42nd. So you have to keep that straight. The power, you add 1 to, which is 43 for the new power, and then you multiply by the reciprocal of the power. So you do 1 over 43 times 1/3. 43 times 3 is 129. So this is 129th times u to the 43rd. Our integral sign has disappeared, our last one, so we put plus c there. Now we substitute back in, u is 3x plus 5, and we see that this is our entire family of antiderivatives. And again, you could check that. How could you check it? Well, one way you could check it is take the derivative of this. If you take the derivative of this, you should get derivative of your answer. The derivative of plus c is always 0. And you take the derivative of this, we're going to need to do the same substitution and use the substitution rule, in other words, the chain rule, when we're going backwards to find this. And what you should find when you get done with this is the integrand here, the part right here without the integral sign of the dx. That's what you should end up with. And of course, that is what you get. The derivative of c is 0. 43 times 129th is 1/3. Then you've got u to the 43rd, so that's u to the, you got u to the 43rd, so it's 43 times u to the 42nd. So you get a 3x plus 5 to the 42nd. The 43rd times the 129th makes 1/3. Now you had a u substitution here, so you've done the chain rule. You have to multiply by the derivative of the inside part, which is 3, and that cancels the 1/3. And sure enough, you're right back here where we want to be. So that's how you can check it. How can you check it using your calculator? Let y1 be the answer and put any plus c you want, like 0, or any other number there for a constant, as long as it's actual constant. Put this formula in, Let y2 be the numerical derivative of y1, and then let y3 be your original function here, 3x plus 5 to the 42nd, and the tables for y3 and y2 should match. Alright, next problem. The family of antiderivatives, or the indefinite integral of x squared over x cubed plus 3 dx. Once again, I'm going to ask you to do that one on your own. See if you can figure out the right substitution and come back and check your answer when you're done. Press pause now. Well, one thing that we can try to do when you have a fraction, sometimes this works, not always, but sometimes it works, is just try letting u be the denominator and see what happens then. If we let u be the denominator, which is x cubed plus 3, what's du? Well, the derivative of 3 is 0. The derivative of 3x squared, derivative of x cubed is 3x squared. So du is 3x squared dx. Okay. Well, let's see. Oh, look at that. We're lucky. We have the x squared and the dx. Now, had there been something else in the top besides an x squared, this technique wouldn't have worked. But since it's an x squared, we're good. Now, we don't worry about the 3 so much because we can fix that by putting a 3 here and a 1/3 here. But, for example, had it been just an x there, this technique would have not quite worked. We could have inserted an x and made it x squared, but we'd had to put in 1 over x. That'd be fine, but we couldn't pull the 1 over x out front. So the reason this works when you're off by a constant is that the constant multiple rule says that we get that 1/3 out of our way. Now, by inserting that 3 and that 1/3 to balance, we can group the 3 and the x squared and the dx over here together, and all of that gets sucked up into this du here, just like the x cubed plus 3 gets sucked up into this u. Okay, so the x cubed plus 3 is u, so this is 1 over u, and all of this part right here is du. Well, the antiderivative of 1 over u du is the natural logarithm of the absolute value of u. So we have 1/3 natural logarithm of absolute value of u plus c. Of course, u is x cubed plus 3, so we leave that there. Now, had this, for example, been an x squared plus 3, which is always positive, we could have dropped the absolute value. But since x cubed plus 3 sometimes becomes negative and sometimes positive, we have to leave that absolute value there. It's important. Notice that the original function is defined everywhere except when x is the cube root of negative, cube root of negative 3, or the opposite of the cube root of 3, whichever way you want to say that. And then that makes this thing 0. And of course, that makes dividing by 0 here, which is undefined. That makes logarithm of 0, which is undefined there too. So both these functions are undefined in the same place, but otherwise things work out nicely. So we should be able to check this by doing a derivative of this answer and get this integrand right here. I'll leave that to you as a check for homework problem. Okay, let's try another one here. 13. X cubed times 3 plus x to the 4th to the 6th power. Okay, see if you can do that one on your own now. Press pause, come back when you're done. Press pause now. Well, obviously, when you look at this, x cubed times 3 plus x to the 4th to the 6th power, okay, that looks a little complicated. It's definitely not one of our basic rules just right off the bat, so we need to do some kind of substitution. Again, one of our little tricks is that we see that when we have a variable base and a constant exponent, one thing we can try is to let the variable base be u. Now, when I say try, I really mean that. Things have got to work out correctly on these substitutions for things to work out. So when you see something like this, you try a substitution, you put it in, work out what u is, what du is, you decide what u is, you work out what du is, make your substitutions, and then hopefully what's left is something that's easier to work with. Sometimes it works, sometimes it doesn't work. Okay? Hopefully on the homework problems that we have, it will work out because they're designed that way. So if we take 3 plus x to the fourth and let that be u, now we have to figure out what du is. Of course, the derivative of 3 is 0. Derivative of x to the fourth is 4x cubed, and then of course we always have our dx. So du is 4x cubed dx. Well, oh, look at that. Boy, things worked out just perfectly for us. We have the x cubed right there. We put that with the dx. Still needs a 4, but that's not a problem. We can balance that with the 1/4 out front. Now, this part right here is du. And this part right here is u to the 6th. So the 3 plus x to the fourth is the u. So when you have 3 plus x to the fourth to the 6th power, that becomes u to the 6th. And the 4x cubed dx is grouped together, which together becomes du. Oh, well, now that is easy to do now. The antiderivative of u to the 6th du is just u to the 7th times 1/7. So the power goes up 1 to 7. Remember, we're doing an antiderivative here, whereas we were doing a derivative over here. So once again, you got to keep track of whether you're going forwards or backwards on these things. Okay, so we add 1 to the power, which is 7. We multiply by 1/7 times, we still got the 1/4 here that we had to introduce. So that makes 1/28. Our integral sign disappeared, so we put our plus c, so we have the entire family of antiderivatives. Now we have the antiderivative, but in terms of u, we need it in terms of x, so we go back and substitute 3 plus x to the fourth in place there, and now we see we have the final answer. Let's see if we can knock out a couple more here a little faster. See if you can do this one yourself. X squared times x cubed plus 9 under a square root. See if you can do that one. Press pause now. Okay, now if you're back here, the thing to remember, of course, is that a radical, or root, is a fractional power. So this, again, is a variable base to a constant power. We have an x cubed plus 9 to the 1/2, which is why I rewrote it here. So again, when we have a variable base constant power, thing to try is let u be x cubed plus 9. The derivative there then is 3x squared plus 0 times dx. So the derivative is du is 3x squared dx. Well, once again, we have the x squared and the dx. We just need to put a 3 in, balance it with the 1/3, and the part in parentheses becomes du. This first part becomes u. Part in parentheses here is u. The part over here in the parentheses is du. And so we get u to the 1/2 du times 1/3. Right. So the integral of 1/2 u to the 1/2 du is u to the, well, the power goes up 1, so that's 3/2. Multiply by the reciprocal of the new power, which is 2/3. 2/3 times 1/3 is 2/9. Remember, when we multiply fractions, we multiply the numerators, multiply the denominators. And then, of course, our integral sign disappeared, so we get plus c there. And the u is x cubed plus 9. Actually, I had square roots to begin with rather than fraction powers. Personally, I just as soon have the fraction powers, but we typically want it back in a typical similar form than what was given. So I'm going to go ahead and do a little simplifying here before I even substitute. U to the 3/2 power, as a proper fraction, 3/2 is 1 plus another 1/2. And so that becomes u to the first times u to the 1/2, which is u times the square root of u. Or in other words, divide the 3 by the 2, the remainder 1 is the power outside, the quotient 1 is the power outside, the remainder 1 is the power inside. And now I go ahead and substitute back in the x cubed plus 9 in place of u, and that's the final answer there. And let's do one more, and then we'll break and go to another video for the definite integral problems. So the antiderivative of 2x e to the negative 3x squared dx. See if you can work that one. Press pause now. Well, this time it's not the base that was variable and a constant power like that one in 14. This time in 15, we see that it is the well, we have an e, which is a constant, and to a variable power that's a little more complicated. In this case, we're going to let the power be the u. So let u be negative 3x squared. Du is negative 6x dx then. Oh, look at that. We've got a 2 and an x and a dx. We needed to multiply by another negative 3 to turn that 2 into a negative 6. Well, if we multiply by negative 3 here, we have to divide by negative 3 out front, or multiply by negative 1/3. Check it out. Negative 1/3 times negative 6 is positive 2. And it doesn't matter which order we write these as long as its parentheses are in there correctly, so it's multiplication, it's commutative. Alright, so now we have e to this power. The power is u, so this is e to the u. Part in parentheses here, negative 6x dx is du, and so we end up with the original integral is equivalent to negative 1/3 the integral of e to the u du. Alright, that's probably the easiest integral of all. The antiderivative of e to the u is e to the u. And so we have the negative 1/3 out front, so our antiderivative, our family of antiderivatives is negative 1/3 e to the u plus c, and u is negative 3x squared, and there we get it. Again, if we were going to check this, we would do I'll let you check it on your own, and you can do it with a, you're going to need a u substitution, i.e. the chain rule, and it should work out correctly, and you can also check it in your calculator. Okay, come back in the next video and see if you can work these. We'll work these three these three definite integral problems, and I strongly encourage you to actually just work all three of those out before you even come back. See you in the next video.